should start recording. So yeah, so let us start the business. Yeah. So from the topic or sort of the shared screen, you can see that I mean, brief discussion on these two lectures will be sort of NLP applications. So the last part of it from in tomorrow's lecture, maybe last half an hour, we will sort of discuss a little bit on language and vision, one or two small applications. So we will try to club things that you have learned. So for example, segmentation, and then sort of, or detection, I don't remember, I think detection, and let's say use of natural language prompt for it, not say fixed classes. Anyway, so we will go into it tomorrow. Okay, sorry. Okay, so the agenda is discussion on unsupervised pre-training towards word embedding. So what are word embedding, what is unsupervised pre-training, and so on, that we will see. But these actually help a lot in basically boosting the performance of these NLP applications. And then discussion on some specific model, for example, Word2Vec, Elmo, and BART. Okay. So resource as usual is this Sergey Levin's lecture on the basically NLP applications, and this is okay. I think I have yeah, I have not uploaded the slide, so this link I have to just change, but it is lecture 30. Okay, now yeah, I think the link is just the playlist link, so it should be fine. Anyway, so let us go or delve into it. So the big idea, as it says, is unsupervised pre-training. So we have seen this, that deep learning works best when we have a lot of data. So we have told sort of many times that okay, deep learning is so doing wonders and so on. So many big models are basically okay, say every day we'll see that okay, this on this benchmark, okay, this model is has been the new SOTA and so on, and it comes with billions of parameters, so many billions of parameters. So I mean, as much we can attribute the success to these big models, I think it will not be or wouldn't have been possible if you didn't have this big amount of data, this huge amount of data. Otherwise, I mean, the potential was always there. So that's the sort of success story of deep learning. And I mean, these all, I mean, many of the methods were sort of coming from a very sort of I mean, pretty early time of AI. So LSTMs, early 90s, even the RNNs were there before that. Then ConNets, even 90, that's also from 90s. But we started to sort of hear about those from say around 2010, 12, around that time. And that actually there were many sort of stimuli to that, and one of them is this availability of big data. So you have big level data. So people, I mean, internet was pretty much prevalent. So there were concepts of okay, say Tarkers, and you can ask people to say level data and so on. So so these availability of level data is one of big huge level data sets. And another is of course the computation. So the computation, the GPUs became predominant in the deep learning community. But the thing is that of course the data has been one stimulus. So deep learning works best when we have a lot of data, and not only data, it's a level data, right? So till now, that's what we have seen. Now, good news, and level means say for images, what class it is, or even say the detection bounding boxes that has to be drawn by some human, right? Or even the segmentation levels that okay, meticulously it has to draw. I mean, some human has to draw the those fine boundaries across images or objects, right? The good news is that, I mean, now the idea is that, okay, so we have seen these success of deep learning, and there is plenty of text data out there. So there are huge corpuses, say Wikipedia and many news articles every day. I mean, in the internet, in the web, you get lots of text data, say the movie reviews, say many things. But there is one, I mean, so one thing that you can think is that, okay, so we have data, and we know for text data, and we know that data is crucial when deep learning works very good when you have lots of data. So why don't we try to, or we can expect this translation of success of deep learning, say in vision, to NLP. But there is a small, slightly subtlety or bad news. That is, most of it is unlabeled, because it is not only data or huge amount of data. It's, I'd say, labeled data that is also important, right? So most of the times you don't have, say, the corpus of, say, translated text. So that, okay, English text, a lot of English text, and the corresponding translations to French or Hindi, right? So that you probably don't have, or you might not have that. Okay, you will have some say recommendations or the movie reviews, but okay, whether it's telling a good thing or bad thing about it, that somebody has not labeled maybe. Okay, so that you need to sit down and employ some human to label it by reading each of the reviews and so on. So there is like 1,000 times more data without labels, say valid English text in books, news, web, versus labeled or paired data, say English or French translations, as I was saying. So, but you will get these just the valid English text in books, news, web, or valid say French text. So can we sort of exploit these things? So the big challenge is, how can we use this freely available and unlabeled text data? So freely available is as true as unlabeled. So that's why these are sort of bold-faced. So how can we use this to help us apply deep learning to methods in NLP? So that we will be discussing sort of most of this lecture, and sorry, all of this lecture and most of next lecture also. So let us sort of start simple. So first thing is that, okay, if we want to use say this huge corpus of text data, we need some way to basically represent words. And not only that, actually this unlabeled data can help us in learning good representations. So when we say started discussing on sequence models or sequence to sequence models or RNNs, we told that, okay, we represented texts in this one hot vector form. That is okay. The size or the dimensionality of this vector will be the number of words in the vocabulary, and the entry, there will be only one, all else will be 0, and the corresponding index of that one will be the index of the word whose representation we are trying to find, the place or position of this word in that vocabulary. So you have just fixed your vocabulary, say 10,000 words, you have fixed the positions of different words. Now in your sentence, you will see, okay, this word comes in, say, 5,012 position. So you will have 1 in that 5,012 position and everything else. And that will be the representation of that word. Okay, so it is not great, but does some good job, and that is not terrible also. Now, why it may not be so useful? It is useful, but what it does not offer is that, okay, there are some words, they are maybe just synonymous, but in terms of this representation, they are very different. I mean, they are sort of no different than some word which is not synonymous with it. So the difference between, say, one word and its synonym is same as the difference between the same word and its, say, antonym, or even some indifferent word. So that is sort of what we mean when we tell that semantic relationship is not preserved. So you don't have this semantic relationship coming or reflected in this representations. So if we can have some way that sort of preserves this semantic relationship, we can maybe use it for better use in downstream tasks. So what are downstream tasks and so on, that will come. But just before that, compare this with say images. The pixels in isolation, maybe just if you think just one pixel, this it may not mean anything, but pixels in say coherence with say its neighbors, okay, it actually means something. The structure actually imparts meaning to it. So it is a little different. These words, word representations is little different from these image representations, only simple pixels. And coordinates, we have seen that it greatly exploits this structure, these local structures, because you are basically using small filters and you are convolving and just getting meaning out of it. So in isolation, the pixels basically is not great. It's not a great metric space. Suppose you just take another image of this puppy, just slightly rotated, or maybe just in a slightly sort of underexposed lighting conditions. And if you take just the difference between the two images, and you will find that the norm is huge. So it's not a great metric space. So in a metric space, things that are close, semantically meaningful, at least for our purpose, they will be close. And the things that are very much different in meaning, they will be sort of that are not similar, so to say, they will be pretty far apart. So this is not a great metric space, but still they mean something, and coordinates actually exploit that structure. So if we can have some meaningful representation of the words compared to these word one-hot representations, maybe if we had more meaningful representation of words, then learning downstream tasks would be much easier. So what can be some downstream tasks? I mean, many NLP tasks. For example, I mean, the canonical example of this translation. So suppose we have some good representation of basically say how the English sentences are formed. So a good language model in English. And suppose we have a good language model in French. And then we can probably use them to sort of fine tune on the limited amount of translation pairs that we have. But to get that representation and get that good language model, we can actually exploit this unlabeled but freely available text data. Because what did we say? We said that, okay, if we have a good English language model, that is how it will just have to understand how the English sentences are sort of, or what English sentences are more probable, just in terms of technically, I'm telling. I mean, we can tell that, okay, how English sentences are say understood and so on, how the structure. So, but it is not exactly the case. So our definition of language model that we have told earlier is that, okay, it will assign higher probabilities to the sentences that are meaningful, that are coherent, that are sensical, not nonsensical, sensical, and so on. So we have that corpus, right? We have lots of news articles, Wikipedia articles, papers, etc., which are full of valid English sentences. So if we can sort of exploit that to get a good, to learn a good representation that will be semantically meaningful, that is, the close words will be closer in that space, and sort of different, words with different meaning will be further apart, then we can use these models to language models to say sort of, again, I'm wording using the word fine tune because it has become so synonymous. So fine tune on your small amount of translation pair data. So what did I say? This is meaningful is vectors corresponding to similar words should be close. So that's what I said earlier also. But just try to think back a little that, okay, you have lots of data, text data, which are valid sentences, valid English sentences, which does not need any level. the only thing you know is that these are valid sentences. And what you want a language model which will learn to generate, say, valid English sentences. Or if I want to be more technically correct, that okay, we would like to have one model, language model, which will assign more probability to the valid English sentences. So we can sort of see that okay, there is a possibility that okay, you have these sentences, valid sentences, and there is possibility further also, that is, if you have these good language models, you can use it to these downstream tasks. So this is what sort of the prelude to what we would like to say delve into. But again, I mean, if you have any questions on this part, till now it has been a little bit on the hand wavy regime, but yeah, I mean, we'll soon go to the technical part. But still, if you have any questions, I can stop. Okay, if not, then yeah, let us proceed. Okay, this is some examples of good word embedding. So this is from, I mean, the word embedding run on some corpus of data, and that word embedding is the word to wake method, and that we will definitely cover today. So if you see that these words, say, so this is, say, paper, salt, mix, put, roll, oven, flour, soft, good. These are all words which are related to, I mean, all are food items related, but these are something related to, say, baking, baking stuffs. Then maybe this quarter, pound, these are sort of those metrics for measuring, say, breads or cakes. Okay. Then minute, boil, say, stand, cook, stew. These slowly, these are again, so boiling or say not just baking, just boiling stuffs. Okay, so these similar words, since they sort of occur together, or occur mostly together in a document or in, say, a paragraph which describes about baking, say, these words you will mostly found. So they have sort of been clustered in one space. So this is the, I mean, high dimensional word embedding, but that is, word embedding basically means these vector representations, right? And but projected to a two-dimensional space. So it may be a 512 or, say, 1024 dimensional vector representation for each of these words, which we call as word embedding, but it is projected to a two-dimensional space for visualization. So these are, say, these similar words, and then okay, say, half, making it half, cut, pieces, thick pieces, and so on, right? So these are sort of again clustered here. Here some meat related words have clustered, and so on. So this is a sort of a corpus on food items, cooking, etc. Similar stuffs you will find on word embeddings of words which are let's say related to aviation industry, maybe. So yeah, so spacecraft, shuttle, carrier, aircraft, these things are here. Maybe flying, flies, wings, pilot, etc. here, and so on. So I mean, you get the idea that similar basically meaning words will be close together. I mean, that is sort of the idea. I mean, if we can have such a representation, that will definitely help in our downstream tasks. I mean, this you cannot get in those one hot representation. I mean, it's like if there are 10,000 words, it will be 10,000 dimensions space, and sort of it is those in different axes, the different words are there. So they are equally apart. I mean, even if it is very close in meaning, or even if it is very far apart in. So if we can use such representations in, say, translation or other, say, sentiment analysis tasks or sentiment classification tasks, etc., we can expect that this can give us better results. Now, how do we learn these embeddings? So basic idea is what we have, why we are seeing repeated. The meaning of the word is determined by what other words occur in close proximity to it in sentences. So it is sort of that idea, this idea we will build on that, okay, I mean, by meaning here you can say that, okay, the representation. So the representation will be determined by what are the words that say occur generally together with the word in question. So learn a representation for each word such that its neighbors are close. So within double quotes, so it is close under this representation. So that is what we are discussing for long, right? So these are, say, three sentences. So government debt problems turning into banking crisis has happened in 2009, saying that Europe needs unified banking regulation to replace the hodgepodge. India has just given its banking system a shot in the arm, something like that. So some banking related sort of documents, from banking related documents, you have these sentences. And suppose we want to find the representation of bank, so we will of course rely on sentences that involve this word banking, and the terminology that we will use, that this will be the center word. So the word that will be in question, or for which we want the representation, and so on. The other words which are close to the word in the question are called context words. So this is a context word, 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 and so on. Now we can define a window. So context words are words that occur within some distance of the word in question. So this is the center word or the word in question. And suppose we are defining a window of, say, 5 words, then basically +5 and -5. So within +-5 distance, all are context words. So these, and these, say these, and these. So it can be that, okay, these words actually occur very sort of frequently with this word banking, and so on. So so this is the terminology that we will use, and we'll see how we basically formulate the mathematical problem, where using these terminologies we will use this fact that the meaning of a word or the representation of a word is determined by what other words in close proximity to it in sentences. Let us proceed. So suppose this is an example sentence where into is the center word, and suppose we have a window of size 2 and this banking crisis turning problem. So it is not that you will learn this from only one single sentences. So it is again you will learn it from I mean huge corpus, and that's why if you, even if you have some noise, maybe that, okay, into is not a very related word always to banking or crisis, but definitely in banking maybe crisis is a sort of crisis, or just say think about these problems. Problem and crisis, they are pretty much similar word. Okay, so depending on the corpus, if it is, say, always says about say banking and crisis or problem, then maybe that, okay, banking, crisis, problem, they will be very close together. But since it has like billions of words, or sorry, billions of sentences, you may not think that, okay, always this I mean banking, crisis, problems will be together, but the words they generally are together, they will have so sort of they will have the similar representation. So it is something like that. There is a saying that, okay, you are determined by the company you keep, right? So that's sort of the idea. Okay, so we denote the center word with C and the context word with O. Let's move forward. So we will cast it as a binary classification problem. So what we will do is that we will take one center word and one context word, and we will ask that, okay, is this context word a right context word or not? That is, what is the probability that this context, this is a context word for C. Okay, so how will we do this? So let's say we represent this sort of denote the representations, this U, O, and VC. These are just two vectors corresponding to O and C. And what are O and C? O and C. Denote the vector representations of the context word O and the center word C respectively. our goal is to learn them. So I have skipped one line, but let's go to that. So we are actually after this. So see, these are representations. Okay. So if this is the representation, that's what we are talking about, right? From the start, that okay, we want to learn these representations for the words. So that's sort of the goal. Now, for every word in the vocabulary, these two vectors are maintained. So we maintain these two vectors for every word in the vocabulary. So if you have 10,000 length vocabulary, that is your vocabulary has 10,000 words, we will have 10,000 into 2, that is 20,000 such vectors that we need to learn. Once learned, we generally get a single representation, because you can think that, okay, why do we have two representations? So there are some other reasons that I'm not going into, but they claim that, and they show it in the paper, at least empirically, that it helps in optimization. So when we will go to say more deep learning based methods, say LSTMs or that is Elmo or transformer, we will see that that is not always required. Anyway, so once learned, we generally get a single representation of the words by averaging these two. So you have two representations per word. So we basically average them. Now, so this idea actually gave rise to the famous word-to-vec model by Thomas Mikolov et al. From Google, and it was a paper, sort of series of papers in 2013, 12, 13, 14, around that time. So I have not given a name of any single paper, but most of the times the same authors, they were there. And it is, I mean, the name is sort of self-explanatory, that it is from a word to a vector representation. So that's why it is the word to vector representation. Now, what did we say? That we will cast it as binary classification problem. Is this the right context word or not? So it will give some sort of a probability between 0 and 1, that whether if it is the right context word, then whether it's a right context word, or if it is a wrong context word, then whether it's a wrong context word. So what is the probability that O is the right word? So we are actually relying on our good old friend of sigmoid function. So sigmoid we have earlier used, earlier saw that it can be very well used for binary classification problem. So and how do I basically find whether it's I mean, O is the right context word? So it's basically right context word. Whether it's right context word to see, then what was the underlying principle? That okay, if it is the right context word, that means it is close to the center word, and if this center word and the context word are close, their representation will be close. So you are basically just taking the similarity measure, just the dot product between these two representations. So UO transpose VC, it's just the dot product, and if it is a high value, then its similarity is high, otherwise it is low. And now you are just passing it through a non-linear activation, because you need to have some non-linearity also to better capture this represented, or sort of so that the model that you are learning, that is better represented. Okay, otherwise this non-linearity will not be captured much. So this non-linearity is this sigma, and it has another dual role, is that it will sort of translate it to I mean, the similarity score. You can think that this is similarity score, UO transpose VC. It will translate this similarity score to probability between 0 and 1. And this is the formula for sigmoid that we have seen. Now, this brings the right context word UO and the right center word VC close together. So this is sort of okay, if it is high, and I mean, when training, you will basically for a particular center word, you will get, suppose this window size is 2, particular this center word, you will take these word, these word, these word, and this word, and these 4 pairs, that is this and this, this and this, this and this, and this and this, you will just tell that this will be high. Okay, so your ground truth for this will be 1, and then you just back propagate with this binary cross entropy, right? So this brings the right context word and the right center word close together. But we are missing something here, that okay, you are sort of giving always, you can think that it's a binary classification problem where you are always giving the positive examples. So it has to, the model has to see what are some negative examples, negative or examples from negative class. So that is what is meant by it when I say that, but we need to also provide some negative examples to learn. So what is, so what we will do is we will basically randomly sample some word which may not actually come from this sentence. Okay, so some random word, and that will be now my O, and I will just tell that, okay, this is my wrong word. And how will I compute the similarity? So I will compute the similarity by same thing, but I will put a negative in front of it. So it will be that, okay, I want to basically maximize the dissimilarity between them. So here I want to maximize the similarity. Here I want to maximize the dissimilarity between them. And just the thing is that you are getting a negative sign in front of the similarity. And then you put it through the, pass it through the sigmoid function, and just this negative becomes right. So here it is negative and here it is positive. So this will push the wrong pairs of words further apart, so which are not related, because remember this O is coming from some random sentences. Okay. Okay, you may think that, okay, that this random sentence some random sentence, the word randomly that is chosen as O in the second case, that may be related to the C. But yeah, I mean, since I mean it is a huge corpus, you can, I mean, there the chance of that being a context word or really related word will be very, very low. And that is the sort of beauty of having these huge corpuses. I mean, even if you have a few noisy examples, it will not matter much. Okay, so for every center word C, so for every center word C in all those sentences, and every context word O with some window size, we will add the right log probabilities. By right log probabilities, I mean the log probabilities corresponding to the corresponding to the case that O is right word. And then for some randomly sampled word, as I was saying, for the same center word, we will add the wrong log probability. There is this, and then we will optimize this. This is the way. So this sum is sorry, this will be maximized actually. Correct this over the word representation. So you will be, and these are your learnable things, that these are the learnable representations that your goal is to learn this, and those two basically are I mean the probabilities are summed together. So this is for the center word, the corresponding context words, and this is for that center word, the corresponding wrong word, which is randomly sampled negative words. So this is sort of the word to vec summary. How you basically get it. It is P of O. Oh, sorry. The right P of O is the right word given C, that is the right context word. This is given by the sigmoid, which is formulated by this. Similarly, O is the wrong word. You randomly sample some wrong words from other sentences of this C, and you get this. Then you sum and maximize this. And I mean, if you just put this from here, you get this and this. And you run this optimization and get this U1 to UN and B1 to BN, for N is the total number of words. And as I said, the representation of the word is then your average of these two. So now what you can do, yeah, okay, this is oh, where are the examples? I think I have a, okay, I will go to there in sort of laptop, because I think somehow I have just a second first, yeah, the non-updated one, or have I put it later? Yeah, I have put it later. Let me just quickly find it. Where did I put it? Okay, just give me a second. Oh, I think I have sort of forgot to put it inside the yeah, forgot to put it inside the slide. So I'll make changes and but yeah, I'll show it in from the sort of okay, one second, just I'll unshare it. One second. Yeah, in the meantime, I think I have one question. So yeah, Rishabh, I am asking you to unmute. In the meantime, I'll just
So the final vector for the word will be u1 to un or v1 to v1. There are two n number of vectors will generate. So sir, what we will use for the final vector representation of our words?
yes, that's what I said, right? You will take the average. So you have u1 and v1. The average of that will be the representation of the word one. I mean the first word. Okay, so let me actually share from my laptop. I have taken those slides, but I have sort of forgot to put it in this PDF or this slide. One second, I have to unshare. Okay, now if I share from here, yeah. So so what is happening here is that this is some examples from the paper itself, and I'm just taking it from Sergey Levin's slide. So what this means is that, I mean, this sort of shows how can I say, the algebraic relationship that sort of emerges from these learned representations. So if you think that, okay, that this is the representation of the word man, and this is, I mean, these are again some very famous examples that has been given in the paper or even the blog that came accompanying it. But it is not always this nice, but let me discuss about this. So this is okay, so this is from so this is the representation of man, and this is the representation of woman. So if you sort of subtract the representation of woman, or sorry, man from woman, so you get a vector which is in a sense directing from man to woman. And now if you add this direction or this vector to some masculine word, say uncle, you will be very close to the representation of aunt. So some sort of an algebraic relation is sort of getting revealed here. And if you add this man to woman vector to king, you will end up, the representation will end up very close to the representation of queen, and so on. So this is, as I said, is not as nice always, because yes, I mean, they are sort of the proximity does not always mean sort of linear relationships or sort of linear algebraic relationships. So, but yeah, I mean, these are again some very cherry-picked examples, and yeah, this has been shown. Now, this is also another one where they have sort of computed the 6 billion word corpus. The Word2Vec, I mean, after training Word2Vec model, then they computed on the 6 billion word corpus of news articles. So in these news articles, you have these common capital cities, name of those countries, the currencies, etc., etc. So how you actually interpret this is this, that okay, you have this you take this word, say Greece, and you basically subtract Athens from it. So you take sort of the country name, and then sort of subtract this its capital. You get a vector which is sort of directing from Athens to Greece, or so common, or the capital city. And then if you add this to Oslo, I mean, you will end up a representation where the nearest neighbor of that representation or the nearest vector that you can find from word to vec is Norway. So this way you can show that okay, it is basically learning some meaningful representations. So yeah, I mean, you will find more sort of examples in this paper and so on. So before I go to the next part, if you have any questions, you can please ask. Yeah. Yeah, Kaushik. Yeah.
Sir, regarding the U0 and VC, for the context words, say for example, in your earlier example, the banking may have 4 context words, like if the neighbor is 2.
Banking.
You were showing the neighbors, number of neighbors.
Okay.
So, or any sentence for that matter, say if the number of neighbors is 2, we have 2 context word we are evaluating on
Yes.
the left,
Yes,
and
yes.
2 on the right.
Right.
So
right.
that way, we will get 4, 4 vector representations for context word, and 1 vector for the center word. So how are we getting 1 vector for center word and 1 vector for the context word?
No, this is say, I mean, in a batch, what you will do is that you say decide that okay, what will be your batch size. So you will be taking this say context word. Suppose your window size is 2. In that case, what you see that okay, maybe you okay, let me try to make this a little simple. That okay, you will say choose 5 context word from 5 different sentences, or even 5 context word from one single sentence. Just for the ease of or the convenience, I mean, let's think that okay, you take 5 context words from 5 different sentences, and then for each of them you will get 5 center words from 5 sentences, and for each of them you will get 4 context words. So how many it is you are getting? So 20 plus 5, 25. And then what you will do is you will get so you are getting 20 context words. So you will take 20 wrong words from just sampling random words from the sentences. So you are getting this 40 and 5 of this context center word. So total this 45 will be sort of your batch size. For those many words, you will run 1 iteration, and then again you will go for other words in the sentence and go for another iteration, and so on. That will do it ultimately. Okay, I mean, is it a bit clear? I don't see Kaushik. Oh yeah, I have asked you done. So is it a bit clear?
Yes, sir, clear. So then the example which you gave, like if there is a 10,000 word corpus, total we will have 20,000 vectors.
Exactly.
So then the vectors may be more than that.
No, you are taking, I mean, the vectors are corresponding to the word. So if you go to this slide where, for every word in the vocabulary, these 2 vectors are maintained. So it is, no, this is for every word. So you initialize, so if you have 10,000 words, you initialize with randomly 20,000 vectors, right? And each word will have sort of 2 vectors, one U, one V. Okay, then you just compute, you take those 45 sort of words, right? And then you compute these pairs and so on to compute. So I mean, I'm not getting, why are you telling that it will be more than 20,000? I mean,
okay, I got it. I mean, the way I was thinking is that like the context vector, you get 4 context vectors. If you look at banking versus problem and crisis and all of that, so, and you have 1 center word, so you get 1 center vector and 4 context vector. So I was thinking like for 10,000 words you get 10,000 plus your window size.
10,000 is your sort of world of words, so you don't have any other word other than say 10,000. So that is
right. Understood. Yeah.
Okay.
Yeah. Okay.
Yeah.
Yeah.
So let me quickly go to the next thing. At least let us start. So I will stop share from here. And I'll again start sharing here. Yeah. So so now this is the issue. Let us see. So word embeddings associate a vector with each word. That's what we have seen. This can make for a much better representation than just a one-hot vector. So one-hot vector had some problems of does not preserve the semantic relationships and so on. So that can be much better. Now there is one problem that okay, the vector does not change if the word is used in different ways. So if the word is used in different context, again the word context I'm using, but maybe the ways is the word that will be better. If it is used in different ways, still you get the same representation, because what will you do? You will just have that u and v vector. I mean, it's a stored vector, say in some table or something, and then you will find that okay, what is the representation for u representation for this play, word play, and v representation for this same word play. And for both the sentences, it will be u play plus v play divided by 2, right? For both the sentences. Though it should actually think that, okay, you can or sort of visualize that, okay, if I am using in the first sentence as a verb and in the second sentence as a noun, and even in very different meaning, then they should be a little different. I mean, that definitely will give you better down the stream tasks. So I have not told about down the stream tasks. So what to make? Let me sort of take the tell this quickly. So what to make representations after you get these representations by averaging. So for 10,000 words, you will have those 10,000 representations, and you can then sort of replace the one-hot vector representations in your say sentence translation. Or you can say concatenate with your one-hot vector representations in some way, and then you just train your translation model, maybe the transformer, maybe the simple RNN models, and so on, and that generally gives rise to better performance in translation and so on. So that is sort of the down the stream task. So the down the stream task is the translation, or maybe the sentiment classification, or there are other tasks also that we will see later. Okay, so if we now have these representation of or sort of these two sentences, not representation, these two sentences, and we don't have a different representation for the same word but used in different context, then we can think that okay, the down the stream task will be can be bad actually. Okay, so this is sort of the motivation for what is called the contextual representations. So same word to word representation, even though they may mean different things. Now, can we learn word representations that depend on context? That is how basically you are using it in the sentence. Okay, so it should depend on the sentence. So high level idea, how do we do it? Is train a language model. So you just train a language model. Probably language model does not have anything to do with it, but if you think that okay, you have a language model, then you run the sentence. Suppose you run this let's play basketball, and you use the hidden state corresponding to this play word. Suppose this play word sort of was input here. So you take the hidden state and then use this as your representation. Now you will be sure that if you run this sentence, this is where play appears, and previously it was what, let's, and so on. So it will be different than when you ran, say, I saw a play, because then your representation you will be taking from it, and it is a function of all the previous words. Those are very different from the previous word in this sentence. So that is the sort of high level idea that we will do to learn the contextual representations for the word. So train a language model, run it on a sentence, and use it seeded state. So if you want to have a sentence level representation, or not a sentence level, in a more particularly say context aware representation, that okay, if this word is used in this sentence in some way and the same in a different sentence in a different way, we should have different representations. So now the question is how to train the best language model for this, and how to use this language model for downstream stores. So these are the two things that we will sort of discuss starting tomorrow. I'm just giving the names here. So embedding from language models is ELMO. It was a paper from Deep Contextualized Word Representation, which is NAACL 2018, which is North American Conference on Linguistics, Association of Computational Linguistics or something. I mean, it's a very prestigious conference on NLP. It's a bidirectional LSTM model. Now, what is bidirectional? What we mean by bidirectional LSTM? Normally, it is not that. It is just two different LSTMs and trained sort of in one forward direction when you are feeding the sentence in the normal forward direction, and the second one is when you are feeding the sentence in the backward direction. So it's not exactly same as what we mean by bidirectional LSTM, but it's an LSTM model used for context-dependent embeddings. And the other one is BART, which is bidirectional encoder representations from transformer. So it uses this ELMO uses LSTM, and this uses transformer. So BART, the paper is BART, pre-training of deep bidirectional transformers for language understanding. So what we will see that it is sort of only it's not an encoder decoder architecture from transformer. You can think that okay, you are taking encoder and make some changes on it, or maybe you are taking a decoder and making some changes on it. And it's a transformer language model for context dependent embeddings. So this is where I will stop today. We will start with ELMO tomorrow. Okay. Any questions on today's topic? Okay. So if not, then yeah, tomorrow we will sort of continue this. And yeah, I shall definitely let you know about the exam slot and etc. tomorrow. Thanks.